Hello everyone. Welcome in this presentation where I want to talk about the Cypress PSoC6 that I got, where I do audio or sound processing and output of that. Why did I make this video? Because 3 weeks ago I got this board, I started playing with it, and it seemed to be quite difficult to get audio processed, but not technically, but to understand what it does, why it does it that way, and how it actually works. What are octaves? What is a Fourier transform? And in the end, I got a working project, and I don't want to let you go through all that mess again. So I want to share this with you. So to start with that, what did I use for the hardware? I got a Cypress PSoC6 MCU, so a board. Actually, it was a prototyping kit, so this, I can show it to you. Is this board, which is basically a breakaway board with these sensors on it. So you can see here, it is a board that is the middle part is the actual processing board. The processor module solid on it at this side. You have some buttons, reset and a user button. There's an LED over here. Then you can break off these other 5 boards, or you can leave them on, what I did for now. The first one that I use here is the programmer board, programmer and debugger, and that's how you upload your code to this board. Then in the middle there's an SD card and a memory chip. I don't use that, but of course it's there. Then we have a small top board where you have 2 microphones on the corners and a thermistor, a thermometer. The microphones are PDM, and I will go through that in the slides, what it means, how that works, and what it does. Then in the corner there's a board for which is the pin breakout is the official method how PMod breakout boards do work. So you can solder your headers on, and then you can click in other components that are standard sized and standard configured into these. And then the larger one here that we have is a CapSense board. There's a slider in the middle, and there are buttons. There's a little thin layer on top of the board that feels or senses where your finger is if you move over it. So it knows if you're in the 1st or the 5th and how far in these boxes you are for the slider. And I use these as well in the project. So the ones that are highlighted is what I'm using. So audio processing, there's a microphone. And then what? Then, well, there are some words here, and while going through the project, I used all of these aspects. And when I first did see them, I was, what is this all about? And I did a lot of reading, YouTube watching, more reading, testing, trying, and everything. And that's what I want to highlight for you now today. So to start, do we talk about sound or audio? Where sound is the word that we use for vibration of air or fluids, and our ears and brains can change that into tones, or change. They perceive it as tones. So we can hear something, sound. We can hear a radio. We can hear somebody sing. We can hear music. And all these sounds, when we make a record of that with a microphone, we put them on a CD, we send them over the radio. We process it as data in a computer. Then we call it audio. I use both words in this presentation, and I try to keep sound for when I'm talking about what your ears are doing, and audio as soon as it passes the microphone and does get into my project, then I use the word audio for that. So the simple basic things of sound is that if you have an instrument, the blue wave in the top picture, a flute, and you play it on one specific tone, then you can say that's one frequency it plays at, and the loudness. The frequency means the number of waves it makes per second. And the pressure, the loudness, is how high is the wave. So we can say this flute is quite a number of waves. That's a high frequency, but the pressure, the loudness is low. Where this yellow one, and I said it might be a piano in one of the notes it has, it's very loud, but it has a low, so it's a bass sound that you hear. In reality, it's not exactly like this, but this is a way how to make it easy to understand what frequencies are, because a flute does not have one single frequency. It has a frequency band of multiple bands per tone. But that's the detail that I will save you for later. If you think about air pressure, because if in fact, if all these three instruments play at the same time, our ears can, because we see that that somebody's playing a flute, we know it is the sound of a flute, and because we learned it, maybe you heard it before, and then we know what I now hear is a flute, what now hear is a piano. That's a car, and that's what we do in our brains. But in reality, the air is just vibrating, and because all these three play at the same time, the air is making more of a pattern like this, and in fact, it is the sum of the three waves together. Now we can see here we have a dip, and that is true because it's on the 0 point here as well. Here we have a higher one, and that means that yeah, all the three are in quite a high range at this point. So it is a presentation, and this is what a microphone knows, because a microphone doesn't know if you play a flute. A microphone just gets an air pressure in as an input. So then what, we started with ears, because that's where we say, we talk about sound. What do your ears do? Say, well, this is an ear, of course, it is an ear. And the air pressure comes in, so that green line, because it doesn't know an instrument, it only doesn't know an air pressure, a sound wave. In the middle of the ear, we have the membrane or the eardrum. And that starts vibrating based on the input it gets from the outside. That vibration is translated to these three bones in the middle of your ear, and these three start vibrating the front of the cochlea. And cochlea is, in this case, it's just shown as one turn. Some show it as a snail or a worm, how you would say it. And it's filled with fluid. And the fluid starts vibrating as well. And based on how the frequency of the sound waves that come in, it vibrates, and it knows on which part of the cochlea the sound comes in. It can tell the brains what it hears for the frequency it has. But it doesn't know yet. If you're hearing a piano, a flute, a trumpet, a car, an explosion, nice music, voices, whatever, it just tells your brain, I hear something at this frequency. So now we'll go to your microphone. And if you look at the board, let's see how close by I can get it. There's the two microphones. It's the little two square things here at the ends, the little boxes. And that is actually a microphone that looks like this. We call it PDM microphone, and PDM is in fact based on a MEMS microphone. I will show that. But these boxes it's a little box, and there's a little hole in the middle. These microphones have a frequency of 20 hertz to 20 kilohertz. And one slide back. What did we say? There's 20,000 hertz, 20 kilohertz as the max. And well, actually in the middle here, it's a 20 hertz that our ears can hear. So the microphone we use on this board is the same frequency plan as that your ears can hear. So this type of microphone, and this is a more detailed sketch of what is inside. So we had that little hole in the top. By the way, these type of microphones can also be upside down, to say. So then the hole is through the PCB, and then soldered onto another PCB, and then there's a hole through that. And you will see that as well in a lot of devices you buy. But the sound comes in, and it comes here at the MEMS diaphragm, and that's like your ear. It's a membrane, and it starts vibrating. That's what registered air pressure. And with a wire, it goes to a chip, and the chip is an ASIC, and the ASIC is translating this signal in what we call a PDM format. So what is PDM? Well, the top one, the barcode. And in fact, this is little pulses of high and low signals, and it's digital. And why is it digital? Because that's the easiest way how in, for example, your mobile phone, this chip can send his audio to the phone chips, and the phone chips will do the next step with it. But in fact, the microphone did hear this wave. And this is what we call PCM, the pulse code modulation. And that is what we need for our projects, because this is used for information where, in fact, it's the same information, but then we would have to do a conversion from here to there. And one of the good things of this Cypress board is that they deliver a ModusToolbox with it. And the ModusToolbox has a lot of components and little tools that are pre-coded for you and that you can use to do things. And one of the things they deliver with that is a PDM to PCM processing. So we get a nice graph. You tell the microphone what kind of audio you want. In my case, I said I want a 44,000 kilohertz, which is a CD recording quality. And I want to have 4,096 samples each second. So that tells the number of recordings we get. And we want the output in a 60-bit word length, which means that the way how it sends you the data. So you tell something about what you want to get, and that's what you get back from the tool. So if we quickly think about sounds around us, we hear a lot of sounds, and our brains would say, hey, it is in that frequency, and then that frequency, this is so loud, this is so loud. And it kind of plots us a big map of all the waves, all the hertzes we hear, which all, it still doesn't tell us anything at this point, but your brains know what to do with it. If we look at what the microphone tells us, it looks more like this, which is one big graph of up and down going waves, and we have to do something with that because this is coded of these sine waves from what our ears do perceive. And that's one of the things that I wanted to work through in this project, to show you a bit of, you hear low noise, you hear high frequency noise, do you hear sound? Actually, I wanted to show if I hear a bat, but a bat is on about an 80 kilohertz sound, so that's way above what our ears can hear and what our microphone can hear. So I first wanted to dig through this, and that's where the first thing you have to do to strip this down back into waves like this is to transform it. And in the world of mathematics, there's always somebody who invents something. And in this case, in 1822, the Fourier transform was invented. Well, actually, at that point, the person who invented this, he made this to analyze the heat and loss of heat in water. And he found that you have these waves, and if you put a formula, a construction over that, you can get your frequencies back. And he does it based on the center of mass. There's a lot of the information on that on another YouTube video that I watched, and I will link it in the description notes. And it gives so much detail about what it does here. I recommend you to watch that because I cannot do better than he can. And if you want to freak out even more on all the little formulas and details, I've also added a series of YouTube videos from the Washington University about specifically Fourier transform, how they work, how you can put formulas through that. I will give you a bit of an idea what it does here. So we had these sound waves that actually, what we showed in the first slides, is that it has multiple wave lengths below that. What it does, it makes to split the data, and it will tell the energy of each frequency on another X of data. So we can know what is the energy of a frequency at each level, and then we can say, hey, this wasn't high energy, then there must have been something on that frequency that was making the sound that we recorded as the audio layer. So we had that orange line received from the microphone, and this Fourier transform will show you something back like this. And it will tell you, so on this, there are some very high energies on these frequencies. And here it's a bit lower, and it's at least you get another level of data. But still, what does this say? Then if you take the one step further there, then you have octave bands. And octave bands is what we call tones, or what we in music know, because you play in a specific octave your music. And that is a band of sounds and a band of tones. And if you look at these graphs, they look like equal boxes, but actually the X is a logarithmic calculation. So we have the 1 kilohertz, the 2 kilohertz, 3, 4, 5, 6, 7, 8, 9, 10. So the steps are getting smaller, but the data within there, so that means there's one step here, so one recording and one. This octave is in the middle as a 1 hertz. The second one is 2. The next one is 4, but it actually looks at 3 to 5. So the band of frequencies, the number of data points, the input we get is getting us a bigger number of data. So what we're doing is what you get in from the Fourier transform, we split that into these octaves. But you can see each time the octave gets wider, and that's because of these more points that are in this, because this is not a logarithmic shown data points. This is 1 hertz each. But based on this, I can now start telling you where is the most, the loudest tones. And you can look at it in 2 ways. You can say, well, I sum up everything between here and there. And that's my total audio pressure of this octave. I can also do that, summing that up and divide it by the number of data points I have. And then I can look at average audio, energy points. So if I would just sum it up, I would get something like this. Or if I average, it might also be like it. It shows you what did our microphone capture, and what is the loudness of each octave in the full spectrum of what a microphone can capture for you. But then there's one funny thing with your ears, because a microphone is designed to hear everything it can within its technical range. And they make microphones in very high quality, so that means that it hears everything in an almost or 100% range for you. But your ears, and that's that cochlea, it is built to hear what is important for your ears. And at the outer sides of the cochlea, I would not say it's the quality of hearing, it's the way how it's translated, and it's using it for signaling in your brains is lower. And our voice is somewhere here in the first, or actually at the end of your cochlea. And that is the most important for us. And you will see that the higher the frequency gets, we don't really hear it. And if you're growing older, then actually the highest frequencies, you get less sensitive for that. So to compensate for that in your readings from your microphone, we do what we call weighting, and that is frequency weighting. And there was made a graph of that, and that's a calculation, and that's again on the logarithmic scale, where the 1 kilohertz is here in the middle, and that's a 0 point for all calculations. The green line is what your microphone is about to register. It might be a little bit better on some points or less good at some points, but usually that's what we call the Z weighting, the 0 weighting, and that's what a microphone does. But your ears is the red line. And that is what is important, because voice will be somewhere here. It is important, but apparently it's so loud that we don't have to amplify it. Actually, we can lower it a little bit. But the higher sounds, apparently our ears are made to amplify these, where after the highest tones, it just drops, and there's no weighting or calculations for that. We don't hear that. The blue line is a C weighting, which we use for noisy environments. I don't use it in this project, but there's weighting data for that available as well. So that means if we look at our graph and we say, well, the actual sound was that high over here, but our ears do have that weighting, and we only hear this. It was a lot of information about audio, about sound and audio, about how to process it with your ears, what a microphone does it, how do you get from that pressure signal back to waves and octaves and to weight that. But this is the basic of what you will need for going further with this, because one of the things, and I will highlight later, is what can you do with specific models for different people, and I will get to that. First, a bit of technology, because that's also what it's about. If you get a programming board and you want to build something, I'm using the FreeRTOS, and that's a real-time operating system, but a little bit on what is the difference here. If we look at classic single-threaded old, well, say if you get an Arduino board and you just take the Arduino programming and you don't do anything fancy, you will start with setting up or making a setup loop. And in the setup, for example, in my project, I would make a Wi-Fi connection and I would get a time from a time server. And you only do that once. So that's your setup procedure, your setup loop. And then you go to the normal loop or main. And like what it said, it's a loop. It's what it does. It goes through the program. And when it's at the end, it will start over again. And that means that it does all tasks one by one. So I can check in this case for the slider. Is there any touch on the slider? No? Okay, next step. I'm going to record some audio. And I will wait till the recording is completed. Then I'll start processing it and I will show my data. And I will send the data to Influx stacking because I'm collecting that later more. And then I, once in so many loops, I send the data to the server. Then I start again. Is there a sliding? Oh, somebody touched the slide. And at this moment, because if it was halfway during the audio processing and I let my finger go off, I would miss the slide. And that's where we come into the multitask at the time, like what an RTOS can do, a real-time operating system. And in fact, it still does one thing at a time, but it does divide all the tasks in little pieces, and it knows about priorities, so it knows what it does to do where and when, and it will just do 15 microseconds on the caption slider, 15 on the audio, and 15 on the influx, and it will manage this for you, but in the end, it does kind of do it all at the same time. So in my example, I start with, because that's what we said in the sub loop, I start with the Wi-Fi and the time processing. And after that's done, I will put these into sleep. And I will keep them because if my Wi-Fi drops, which might happen if I get too far out of reach of my router, then it will start that step again. But it can keep that in the process because it doesn't take time. It will sleep and wait till it happens. I think that the other things I do, and I've divided that in 3 tasks, is looking at the caption slider and button, recording sound and audio and processing that, and an influx task that waits for data, and when there's enough data, it uploads. And these are waiting for each other, they're just continuously busy, all 3. And only at the point where it needs to do something, it will pick up the task, and the FreeRTOS will decide which one can do which bit and how that works together. Then I want to show you a bit of the programming code that I use here. And the tool that I used is the Eclipse IDE that I got, that comes with the ModusToolbox as one of the standard programming tools. You can use it in other tools, but I said, well, this is the standard for now. Start with it and see how easy that is or how difficult it is. I have to say the Eclipse IDE is a very powerful tool, way more powerful than I personally need. And there's so much you can do with it. It was a bit overwhelming for me. And I think I have to watch some instruction videos later for, well, what can I do more with it? Show what it does there. I want to go into the software that we use here. So this is the Eclipse IDE for ModusToolbox. My project is set up and it shows me all the files within my project. It also shows a list of tools that we can use for this, for my project that I have active. It shows me all the functions, all the defines, all the the classes, everything that's in my program, I can just click and zoom through whatever I want there. And it's so that's a lot of the powerful things that I did use. Within a program, you have options for debugging, where you can get on the debug lines. You can follow, you can add breakpoints, and it tells you back what values are, where something did go wrong, and that's the part that I didn't use. I think I could do a lot of things with that. It worked this way for me, and but that's the powerful part that you can use with it. So one of the cool things that let's scroll a bit up. So it gives you options for what you want to launch, and I use the top corner part of the board, which is the KitProg programming and debugging tool. So I could say start it as a debugging session, or start it just as a program and run it. Depending on what you want to do, what you need, the data you want to go into, you could use these, and that's the really cool part. There's tools where you can pre-configure the components that you're using. So I could tell here what my cap sense, how sensitive it should be, and some of these additional things that we have here. The Bluetooth, I don't use the Bluetooth here, but you could do that as well. And it gives you links directly to all the documentation that they provide. A quick go through on the tasks that I published them on a GitHub page. You can get to there in the comments of the video, or through the Electron Maker site, where I have a project set up for it. So what I said, I've divided my program in 4 tasks, and I gave them all priority. And I say the cap sense is a very important one, because that's an interrupt, and it always has to register what you're doing. And it doesn't do a lot, because it just waits till he touches. But if something happens, it has to process everything at that point, the touch. Then in my program, I say the audio is an important bit, because I want to register the sound as soon as possible, as quick as possible, and I want to process it as quick as possible. And then I get the supportive task, which is the influx that gathers the data, stacks it, and then sends it off to the server. And I have a Wi-Fi task that makes the connection, but actually the rest of the time, the task itself is sleeping. So I'll set that to a low priority. Then if you look into the code, so the code starts, it prints nice header, and it sets up 2 common queues. And the queues, the first one is used for capsense, and that is just a copy of standard code that ModusToolbox delivers with it. And I made maybe some slight changes, but not big, so I'm not going to cover that now. The one that is important, however, is the influx. And the difference between these 2 tasks is the capsense one is a single element. So you see there's this task that you're giving away to somebody, and you could give him 1 task, but he doesn't pick the task up. But in the meantime, you change your mind, or actually somebody touches one of the other buttons on the capsense. You want to give him to take away the first task and give him a new task. That means if I have a single element queue, it just replaces the pending task. And that's what I'm doing here. It's 1 task. It picks it up, it processes it, and if it's too late for picking it up, there might be another one in there. If I slide my finger over the slider. But the other thing is the influx task, which is gathering the audio readings and is waiting for processing that. And while it's processing it, it's uploading through a TCP connection to the server, so it might take a while. I don't want to lose any of my readings, so I've a queue there, a task size of 200, which means they can enter 200 readings into the queue before it's full. That's way more than I need, because I'm uploading my data every 10 seconds. But yeah, we know what happens. I don't want to lose any of the data. So then I make my 4 tasks and I start them. And after I start them, we should never come back in this first loop or what we have. That's because the scheduler takes care of all the tasks, and if it crashes, and that's the only point where we get back here, and then we can halt the software because it's kind of done at that point. So the 4 tasks, I had a little problem with the Wi-Fi connection, and that is that it doesn't always connect in one go. Sometimes I have to reset the board and try it again. And I found that if I limit the other tasks in what they do, I get a priority on these tasks. And when the other tasks start, they just suspend right away. They sleep and they wait till the Wi-Fi is completed. And with that start, I want to show you here what happens here. So it gets the names of the other tasks for later usage. It makes them sleep kind of again, but that is the others, they should sleep already. But if not, it will take care of that here. And we do that because at the end of this task, I will sleep the Wi-Fi task, and it will only wakes up if a Wi-Fi connection is lost, and then it has to let the other sleep again there. So I wait a little bit till it really sleeps, and then I start the connection to the access point. So the access point sets up the Wi-Fi configuration. It gets initializes the connection manager. It puts in my Wi-Fi credentials, which are in the header file, and it tries to connect to the Wi-Fi. It has a number of retries, 20. Where it tries to connect, and if not, it tries again, and if not, it tries again. And that is for it waits between 2 connections for the number of seconds you fill in here. The Wi-Fi, this is all that you need for connect, because we use all these ModusToolbox tools that we get in that box, and that's one of these great things here. The only thing I specifically do is I make a callback, and the callback actually handles, is there a disconnect? If there's a disconnect, that's not good. So what we do, we resume the Wi-Fi task. So it goes back to the first step again. One of the other things it can tell you if it reconnected, or if it connected, and it will tell you the IP address of the connection that go. So we said we did get the connection, and we returned with a success. So this is complete now. The next thing that we will do is getting the network protocol, the network time protocol, so the time from the internet, and it tells you that's the official time at this, and it returns you a second. So that's the detail you can get to. And we will store that in the real-time clock on the board. This is also a part where I looked at examples, and there's examples that have a full library of a lot of tools and powerful stuff and make connections for you, but I didn't need it that powerful, because all the connection stuff for UDP connection that you need is within that ModusToolbox. So why should I build it again in another way? I just wanted to know, what do I have to send to that server? And what I sent is 3 components: a leap indicator, a version number, and a mode. And that's the only three things that I have to send. I get a response back from the server with way more data, and that's what we unravel here in the second task, because this is the receive callback. It will strip the time, and it will tell you what the time is that it got, and will store it in the real-time clock. And why do we store this at the start? It is because a real-time clock works based on, it keeps the time. It has a very constant frequency to update the time, and to get back to, and to keep that going in a steady way. So you can do whatever you want on your processor, but it keeps the time always in a correct way. But as soon as you unpower the board, it will lose the time. And there's no battery on this board, so it will lose the time. The next time I connect, the first thing I have to do is find the time. And I need the time, and I will show it later, because the packages I'm going to send to Influx need a timestamp, because it needs to know when did you record this audio bit. Going up again. So I'm done with my NTP, and I will resume first the CapSense and the InfluxDB, because they just need to be ready. They will not start anything yet at that point. CapSense will feel if your fingers is sliding or touching buttons, but that's fine. I wait a little bit, and then I start my audio task, because that starts recording and pushing off data to the other 2 bits. and I will sleep my Wi-Fi until there's a connection attempt needed after a disconnect. The slider, it's standard code from the ModusToolbox examples. I think I did only change the way of what it pushes back, because my left and right button actually set the min and the max values of what the slider can do. So I have a slider value of 1 and a slider value of 100, which is what happens within the slider, and that's what it sets. I'm not going into a lot of detail here because it's the standard example from Toolbox. So, okay. Then I have my audio task, and that's where the fun is, because this is talking to your microphone. This is calculating the audio data, and this is sending it off to my Influx task. So my audio is, what is that, recorded at a 44.1 kilohertz, which is CD quality. And because I use this sample rate, I have to say what the clock sync of my processor is. And I want to have 4096 samples of each second it records, or millisecond it records. But that's the based on the frequency, that's the number of samples I want to receive back. These are the two things that I'm using here in my microphone to tell it what is the frequency that I want, and later on I tell it what is the number of samples I want to get back. So the first thing is, as I'm starting my microphone, first a clock that does that frequency for the recording, and that's used for the microphone because that's using the clock in here. So I start the microphone. I start the real-time clock because I did use it in the Wi-Fi connection, but also shut it down there because I don't need it there anymore. And I'm reading if it's working, and I show the current time when it starts. Initiate the LED, and the LED I use to show the sound pressure, to say it that way, of how much audio is, and it's now a red in the middle. If I slide it, well, you can see the sensitivity is getting up and down. And I start my first audio reading here, and there I tell what is my frames, how much audio frames do I want back, what's the kind of the detail that I want to see there. In my reading, I'm looking at a total of, well, I'm reading 11 bins of octaves, but for our audio, for what our ears can hear, 10 bins is more logical what we can do. The synchronized reading is also linked to a callback, and it starts the reading, but it doesn't give you anything back at this point yet. But here I have a for loop, and it checks is the flag of, is the reading complete, is the flag set, and only when the reading is complete. So when this one has a callback, the only thing the callback does is set the flag to true, and then we get into this loop. So we set it to false back again because we've picked it up. First thing to do is get the time from the real-time clock. And that is because I want to know at what exact time was this reading taken. An exact time in this case is a second. I cannot go into more detail of a sub-second, millisecond, nanosecond, whatever, but seconds is enough for what I need here. I'm checking if that second, because I'm doing multiple readings per second, and based on the size of the data that I'm getting, it will tell you how long is between two readings. The smaller your sample size, the quicker the processing goes. The bigger your sample size is, the slower the processing goes. So that's a bit of tweaking what you need there. But for me, that was the logic that I used here. And so I can have multiple readings within a second, which is super detailed, but too much for what we need in my project. So I look at, was there a reading before in this same second? And actually, this looks at, am I in the next second? Because if I'm in the next second, I will average the previous second and I will send it off. The only thing I'm doing here is, because these are the two fields and I'm collecting my audios in, I will look at the number of averages that I got within this second, and I will divide it. And then I will send off, and I will calculate the decibels for that in a function, and then I'm sending it off to Influx, where I send the weighting. So we had the A and the Z weighting, and I will send them 11 octaves and the total, and I will send the time of this reading. And then I'll send it to the end of the queue of the Influx. I'll get to the Influx later. Then we have to reset it because I want to start with new readings to start. So first thing, we said the data we want to receive is a 16-bit integer. And actually I found out that it does process you, that gives you an 8-bit, but that's fine. I can make a float of that at this point, because for our Fourier transform, we need to have floating numbers. Because we looked at that sine wave, there's positive and there's negative numbers. And that's the way how the 16-bit integer is storing data. It's a 15-bit and then signed, or 16-bit signed, which takes off 1 bit for the sign. But I want to convert it into floats. But then I have, because I just converted 1-to-1, I get negative floats as well, where the Fourier transform is working better and faster if it has only positive numbers. So I'm applying a windowing, as we call it. And that's one of the basic functions of Fourier transforms. Let's say if you have a repetitive function that you can use for your data input, then we can decompile or split the input data. And in this case, the repetitive function is sine waves. And that's what the Han window does. Because Han is a definition of how sine waves are looking and what is the range of the sine waves. And it looks at positive numbers. So what Han also does is it makes all our input above 0, between 0 and 1. So it moves it a bit up in the graphing. But that's the first step we're doing here. And the code I used is from the Arduino FFT fast Fourier transform standard code. I didn't make changes. I did strip off what I didn't need to make it readable in this project, but all credits go to them. And same is for computing the fast Fourier. What I do is I tell it the type, I put in my radio, so my audio real data, and there's imaginary data. And the imaginary is more what it will save back, and the number of samples I'm inputting. Then we can calculate the energy, and the energy is splitting all the Fourier transform gives you back two numbers, a real and an imaginary number. And calculating energy is because the real and imaginary is a vector. The energy calculation does take these two vectors, these two numbers, and calculate the vector, which is the energy. Then we sum the energy, and that's what we do by octaves. And in fact, in my coding here, it is a very square octave. So it says it's either one or the other, where in the picture we did see before, the octaves, they have a top, but they are curved going downwards at the edges. So they cross other octaves. And that's not what I'm using here, so that can be enhanced. But for the goal that I'm looking at here is splitting basic audio, the loudness of audio, that's fine. But if you want to do something with that, you have to change the point here. Then we have the weighting, and I want to look both at the Z weighting and the A weighting, where actually the Z weighting is just the reading that I got from my energy calculation. I have to push it through because then it divides in the correct boxes and functions for me. The important one is the A weighting. Then we add it to the average box, which might be 0, which might be because in the same second there was another reading, but it adds it here and it adds another number to the count. And then as a last step, I calculate the decibels, and I do this just to show on screen what the sound spectrum looks at this point. This is only presentation, which is also linking here because this is also a presentation. I skipped the first bin because that's unaudible for us. I'm showing the second to the 11 bins. So I show 10 bins of octaves by going through them and put the number on screen. Then I show the total number because I did do a sum of all, and I place it in the last field as a total. Then I put a little, how we said, a bar to show the pressure of the audio, because numbers is fine, but it goes quite quickly over your screen. And it shows a little bit in a bar of the energy pressure that we have at this point. And I show on the LED, that's what I showed you by holding the board up. Also based on the total volume, the energy of what's going on there. Quickly going through the function of calculations. So the integrator float, I have a bit of code here that shows you the actual input and how I calculate it and how I notice that it's 8-bit instead of 16-bit. And then it converts the sample by the data input, and it will store it in the imaginary or the real data list. Then we get the windowing, which is the hand windowing that we use. So I only left in the part for the hand windowing. There are, I think, about 50 more windowing types. If you want to use them, and of course you should use the official Arduino fast Fourier transform code. The link to their GitHub is in the code. So if you want to use it, want to look into that more detailed, use that. The word weighting is here as well, and that is the weighting of the hand type of the window. It's not the A or Z weighting, this is the windowing weighting. Then it goes to the compute of the fast Fourier transform. That is based on all these formulas on parts of coding, and it's doing very clever stuff. I'm not going in this, but you should go through all these videos that I'm linking as well if you want to have the details there. So what we got out was a real and an imaginary value. That's what we get out of here, of the Fourier transform. And that's what I use here as I take the square of both these, and then I take the square root of them. So that means I first calculate the vector, and then I take the root because I'm calculating energies. I can sum them all the energies, and that's what I said. I put them into the bins, and it's really I take the first one reading, and that's the first bin, so the 16 hertz bin. Then I take the second 2 readings, and that's the 32 hertz bin. Then I take 4 readings, and that is the I think the 63 hertz bin, and so each bin gets larger. And there's two ways how you could look at this. You can sum up all the sounds within one bin and say this is the total sound pressure that I have in this bin, or you can do the same and then divide it by the number of readings so that you have an average. In this example, I'm using the average, but it's up to what you want to achieve with it, which one you use here. Then we look at the weighting. So that's where we have the weighting data that comes in. And the weighting data is stored over here. So I have the A weighting. I've also added the C weighting and the Z weighting. Z weighting is zeros, of course, because nothing happens. The C weighting is what's the interesting bit for us now. Sorry, the A weighting, because this is official registered data that you can get, and that's that graph that I showed you. Of course, you see it's a graph, so it's a curved line, and you could say there's formulas, so you don't need to have this static table of these readings. Yes, indeed, and that's one of the other things that I might want to go through for improving. But it's also a bit dependent on what I'm going to show, because it's based on the order. I'm now first calculating the energy, and then I'm putting the weighting on it. The energy, and then I bin it to the octaves. And then I'm calculating the energy, the loudness. And if I do that per bin, per octave, I should use these preset, literally binned or weightings. If I would turn this around, I would get the energy, so the vector calculation, so the energy. Then I could use the curved and the formula-based weighting, because I have all these detailed frequencies, and after that I'll sum them as octaves. It's a bit to your liking of what you want for the detail. It's two ways, but it makes sense of how you change order at that point. And then as a last step, and I do that, one is for just before uploading the data, and one is for showing the data on screen. That's calculating to decibel, because decibel is something that tells us more than that an energy calculation does. So in the first step, what I said, if after the averaging, I'm sending it off to my Influx task and my Influx queue, and the queue in Influx is receiving the data. It calculates an Influx line that is sent off to the server, and it stores it in my body field. And when it has 20 readings, and I had one reading for A and one reading for Z, so that's 2 readings a second. That 20 readings is 10 seconds of data. At that point, I take the post comment and I add my body to that, and these two together is what I'm sending off to my Influx server. I do that by sending a TCP function, which is here. It makes connection to my server. It makes a socket. It sets up some sockets about timeouts, and then it will connect it to the server. It will try to send, and if it failed, it will do this again. And it will try this, I think about 5 times. If it doesn't work out, it assumes my server is down, and it will continue to the next package because it needs to keep processing the data. But that is why I had the 200 stack size, because I had 20 as an input. I'm trying to send it, and my timeouts is 3 and 5 seconds. So if there's no connection possible, maybe my server is too busy, maybe the Wi-Fi has a bit of slack, it can be anything, then it should not overflow in the stack that I'm losing the data. I want to keep stacking that. And you will see on the command lines when it's sending data, and you'll see it's not really in a steady flow. Sometimes it's after 20 lines, then it's after 5 lines, 5 lines. That means there was a bit of a queuing and there was a bit of a timeout. We'll show that in a bit there. But this is the task that does that connection for you. One of the last things, and that's, I'm not going in details here, but there are functions within these tasks, within the real-time operating system. It's a super powerful and an enormous system. And it's so large, you don't want to load everything by default on your through the compiler and upload it as your program, because your program should be small, because that's making it faster. It's making it smaller to load on your processor. So you tell which kind of configuration should you use. And I had to add some of them. So I will include this in the upload on the GitHub page as well, because I think I had to add some of the suspend tasks or delay tasks for my board to use that on the in the code for the Wi-Fi. So there was a lot of code. I want to show, because I did apply all the other calculations for you, and I want to show you what the output is on screen for me now. And that is one of the ways. While I'm talking, it keeps registering what happens in the background. So you see all these readings, and it is because I'm talking, and the numbers are, you see in the low frequencies, there's not a lot of data. Most voice data is here, and that is because the sound of humans is within these within the 5 octaves, I think about. When you would talk very high and loud, or when you have maybe the sound of your computer, the fan, these little devices do usually have a higher frequency, and it is what ends up in these higher boxes. This is what I say. There's a bit of visualizing. I think if I shut my mouth for some seconds. So you see that it gets to normal lower 2 lines. It's a 20 decibel sound here in the background in my room. But when I start talking, you see these coming back up, and that is the data that we're processing here live. And it's the number of readings is faster here, by the way, because I did that to show you a bit more data that it goes through. But when it would return to my program, in the way that I programmed it in the past weeks, I would set it to the 10-second uploads. So then a bit of showing visualization, because these numbers scrolling by, that's nice and that's fun, and but what can you do with it? What can you show more? And that's what I use Influx databases for. And I will show you, and that's actually one of the things that's also running in the background. So it will show you what I'm talking all this time. So on my Influx server, I have some buckets, and the first one is the audio sensor. I select the bucket, I'm getting my data in and the weighting. And I want to have a weighting data in some of the octaves that we as a human can hear. And for correct grouping, let's do it this way. It now looks back at my data for the past hour. And if I submit, and I get all the data points, and you see that's a lot of data points. It doesn't even make sense anymore. There's so many data points. So what can you do? You can say mean, and mean is the average of what Influx uses, and it does it by every, well, it's so much data now, let's average it by a minute. That's way better. This is because I'm talking all the time, it's a lot of sound coming in. And it's going up from some decibels to, what are we here? I think the highest is about 21, 24 decibels. Let's look at a bit smaller data frame, because then we can see more and average it by 5 seconds. So I don't average it first. This is what happens if you constantly send data, and that's a lot of lines. I think this was when I did shut my mouth for the 10 seconds, and you see there's lower input there. I want to rephrase that 5 seconds based on the averaging now. This is what goes on, but it's still a lot of lines, and I could make a graph for each, and then there's a dashboarding function in Influx, but it's the power of Influx is in storing the data in a database, time-based. It can store on the nanosecond, it can store your data. I just use the seconds here. It's less data points, it's faster, but this is it's powerful already, but it's a lot of lines to say. So let's get back here for a moment. So that would if I use the Influx. But then we also have Grafana, and Grafana is well, kind of bit of in the name. It's graphing, and it's the goal and the power of Grafana is making graphs and showing the data and comparing data. And that's I built a dashboard now, and this is the one from the screenshot. So it's by Octave, it's showing me the data. I use the same colors to be clear, and the lines are relatively low here, but I will show you why. You see at some points, and it happens on all the octaves at the same point, the little drop in sound level. That's because there I was shutting my mouth. What I also did, let me focus on this way first, is a spectrum next to each other. Actually, so I have the A weightings and I have the Z weightings, and it's refreshing. So this is always the last reading showing. This is the last 50 minutes. Let me show quickly in a little other way. So I did lower the lines a little bit because of what I want to show you now. And I don't want to look at an hour. I want 5 minutes and 5 seconds data. But this is what is actually happening right at this point. And I want to show you that it really works. We use for that good old audio, sound, music. And I have to say, I played saxophone when I was 15 years old. all the time it was in a box on the attic, and I picked it up today again to show you something here, and I hope it's visible in the way I want to show you. So wish me luck with this. So the lower tones, to get to the 4/5 octave, I'll try it once more to show a bit more. And if we look at higher tones, they're a bit more in the higher side. It's a bit difficult to see, but you can see, of course, that the pressure of the sound here is way higher when I'm making music there. I think that's one of the things that I want to show here, and I hope it was, well, sorry for the first notes, but that it shows that processing audio with computer board, and that you can really do it, and it really works. And this is 3 weeks of my journey into the audio, and showing that, well, it shows me data, and that makes me satisfied. And well, you can see on the high ones there's less audio pressure, less energy. On the lower ones there's more. It shows my graphs, and this is what I wanted to accomplish in this project, so I'm happy with it. But well, that might be nice on these graphs. So what can you do? What did I do? Well, I did analyze it, and I did learn a lot, and I played with it. You see, I played my saxophone with it. So that's what the program can do now today. But what is now really useful with it? What can you do next with it? So I said, well, I'm averaging my data per second, and at the moment I look at my data in Grafana or Influx. I'm actually averaging by 5 seconds, because that makes more sense for looking at it, because the readings are not really constant here, that they take about, it's about 1 or 2 a second at this point. But if you average it in a wide range, you can smooth out peaks and dips. On the other hand, you're missing your peaks and your dips. It's a bit, you could set maxes and mins on it in the graphing tools. It's so powerful what you can do with it over there. But by having less audio data points and sending less data over your Wi-Fi to the Influx, you can save power. The other thing is, I could collect more than my 10 seconds of data, but collect 30 seconds of data, and then have 3 times less sending of it, which is also consuming less power. But depending on what your goal of your tool is, or what you're doing, that's the kind of things you can think of for enhancing this. And if you store less data points in Influx, it will make it faster, because it doesn't have to look at a lot of data points, but just some. I think that the balance that I have now with 1 data point a second makes sense. And then in my graphing, I can make the data points averaging or summing in another way, and that's what I want to do there. So then I said, well, that's what I highlighted already. My octaves are square blocks. I really look at everything from, I think about 20 hertz to 40 hertz falls within the 33, 32 hertz bin. And so it's really blocks, where you have also octave bands, and that's the curve where my 32 hertz starts actually at maybe 12 hertz with a little, and then it starts summing up more and more of each in each bin, and that's something I could change in my code. And then the weighting, which is now also based on these octaves, so it takes the full octave and it applies the weighting on the full octave. I can use it on a way more detailed calculation up front, and it will both these will change the effectiveness of what I'm actually processing here. One of the other things then what you can do, and I showed that already in the graphs at the bottom. I didn't actually really highlight that now. What I did here in the A and the Z weighting, because this is what my ears are hearing, but this is what the microphone hears. So the line is about here in the middle. And you see the first octave, and that is the 31.5 Hertz octave bin. That is the one that is captured by the microphone, but you see my ears are hardly hearing it. And if you go a bit up, so you see that the weighting applied has less well, you hear less than what the actual sounds are around you. And that is what you could show in a graph here, like here, where, well, the total reading is up there, but you only hear this. And you see the bigger changes are in these blocks and the outer edges of where the octave bins and the cochlea works with. That way, and my microphone cannot do it, and this graph goes up to the 20 Hertz, kilohertz bins. But if you would capture the sound of a bed, and a bed is at 80 kilohertz around that, so you need a special microphone, and your processing board needs to be able to process that. But then you could show that a bed is making sound. So for you, the unhearable sonar sounds you can visualize. But you can also look at, well, what I said, if the older you get, and then you get hearing loss, you're less sensitive to high frequency sounds. So you can then graph out, well, the official reading is this high. This person is hearing this, or I don't want to say normal person, but an average person could hear up to there. So this is the missing bit. And that's the technique you could use for amplifying sounds for people with hearing loss, or warn them when something is around them that they cannot hear. And that's the kind of things you can continue with based on understanding this project, understanding what the sound does, what audio does, what your processing does, and how to visualize and look at that. And I think that's a lot of information, and it's a long video by now. I want to encourage you to look at my project site, to look at the what I've all learned, and I hope it helps you. And if you say that I did something wrong, help me in making this better, because the project that I used to look at had their other ways of approaching data, and I made changes based on that in the way how I look at it, and I'm sure that you're looking at it in a different way. I want to thank you a lot for watching this till the full end of this video. It's long, and I appreciate that you've done it all, and I hope I can help you and you can help me with getting further in this project. Thank you.